Hi. So this video is going to go over how we can take our results from forward, backwards, or central divided difference methods and improve them using a technique known as Richardson's approximation or extrapolation. Sorry, extrapolation. And if you aren't familiar with forward, backwards, and central, I recommend watching the previous video that I have on my channel. Or if you're one of my students, look at note set 5 as this relates to note set 6. But what we showed previously is that if you were to do the forward divided difference method, we would see that our error is on the order of h. And what that means is that if I were to use a certain value of h for one iteration, and let's say I were going to half the value for the second iteration, we will see that our error will also be halved because we're dependent on h. If h is half, the error will be halved. That is also true for the backwards divided difference approximation, where we say that our error is on the order of h. And what we proved using Taylor's series is that for central divided difference, our error ends up being on the order of h squared, which basically tells us that if I started with an h and then I were to half it, comparing h and h over 2, we see that our error ends up being quartered in that situation because we're squaring h over 2, and that tells us that the error gets smaller with each iteration of the central divided difference method. But can we do better is the motivation, and that's what leads to Richardson's. Now, for Richardson's, I'm going to go ahead and use the central divided difference method. For this, you could do either forward, backwards, or central, but the one that I'm deriving now is going to be specifically for central and specifically for the case where we take an h and we half it. So let's remind ourselves of central divided difference. We know that our derivative at some point x is approximately equal to the function value at some point further ahead minus the function value at some point behind divided by 2h. And that's essentially finding the slope of the secant line between a point before our point of interest and after our point of interest. So let's say that I have two iterations at hand. I'm going to say that we'll use some h1 for iteration number 1, and I will do h2 for iteration number 2, where h2 is equal to half of h1. So we already saw that our error for central divided difference is on the order of h squared. And what I'm going to do is generalize that, or I guess make it more specific, to say that our error will be equal to, or approximately equal to, some constant times h squared. Now, if you go back to the previous notes or the previous video, you'll see that we derived this expression from the central divided difference method using Taylor's series. And we saw that this c, which I'm just saying is a constant, this depends on some higher order derivative. And additionally, some factorial, like 3 factorial or something. I don't remember off the top of my head which term it was. But in general, that's some constant, while the thing that we're interested in is the h. So we're just going to say it's some constant times h squared. And what I'll do is I will create a true error for my first h, and then I will do a true error for my second h. But I know that my second h is the same as h1 over 2 squared. That's based on this fact up here. So if I were to write this out, I would see that my true error would be CH1 squared over 4. Now, if you were to compare this and this, we can see that CH1 squared is the same as the true error from the first iteration. So we can just plug that in. And what that tells us is that our true error for the second iteration will be the true error of our first iteration, but quartered. As we already mentioned, this is just more of a mathematical way of showing that. But that's what we discussed previously, that for central, if you were to half H, you would quarter the error. And this is going to be useful for us because the definition of our error, our true error, is the true value minus the approximate value. Where again, the true value is something that we don't necessarily know, but the approximate value will depend on H. So we technically, if we do 2 iterations, we have 2 separate approximate values. So what I'm going to do is I'm going to plug in this expression, TV minus AV, for each of the errors. So I will say that the true error for the second iteration is true value minus approximate value for H2. And I'm going to say that that's approximately equal to the true value minus the approximate value for H1 divided by 4. So now what I want to do is try to solve for the true value in terms of the things we know, the approximate value from one iteration and the other iteration. So if I were to multiply both sides by 4, I get 4 TV minus 4 AV for the second iteration. That's the same as TV minus the AV for the first iteration. And I'll bring the TV on the right over to the left to get 3 TV. And I will bring the 4 AV H2 over to the right. And I can ultimately solve for what these should all be approximates. 4 AV H2 minus AV H1 divided by 3. And essentially what we're doing is we're finding out 2 pieces of information about our function or our approximation. And we're going to use those 2 to help us get a better approximation for the true value. So what I want to do now that we've derived this, and again, this is only valid for CDD and H1 is halved, but you could do the same type of technique for any combination. You could do the same derivation for forwards with the H that's being a quartered or something like that to get a different expression. But for this, it's only valid for central and for halving H. Let's go ahead and do an example to illustrate how we would use this. Let's say I give you a function f of x is equal to 2e to the 1.5x. And I am interested in what f prime of 3 is using central divided difference. And I tell you that h is going to be 0.05. That's my h1. And my second iteration will be half that in order to use the equation that we just derived. So just for comparison purposes, let's go ahead and find what our true value is. Our true value is going to be the derivative of this 2e to the 1.5x. And we know for an exponential, we'll do the chain rule and bring down the derivative of the exponent. That will ultimately give us 3e to the 1.5x. And the true value, which again is the derivative at 3, if we plug in 3, we end up getting that this is approximately 270.304638. And we're doing this for comparison purposes later. So we will keep this nearby. to remind us later what that value was. And note, I did approximately because there were way more decimals that I didn't include. I just included 6 digits after the decimal point for later on showing what our relative errors are. But let's say I tell you to use Richardson's, let's say Richardson's extrapolation, in order to approximate the same derivative. So what we have to do first is use the central divided difference method for h1 is equal to 0.05. That's what I gave you up here. That was given. So what we'll say is that our derivative for central divided difference, I'll just rewrite it to be thorough. If we were to find what the derivative is at 3, we'll say that's f of 3 plus 0.05 minus f of 3 minus 0.05 divided by 2 times h. Again, h1 in this scenario. And I'll do this just now for the first iteration to be really thorough. But if I were to do the function evaluated at 3.05, right, this whole thing is the same as f of 3.05 minus f of 2.95 divided by 2 times 0.05. That is saying to plug in our 3.05, our x plus h, into the original function, not its derivative, because we're trying to approximate that. So if we come back up and look at our original function, that was 2e to the 1.5x. So this is going to be the same as 2e to the to the 1.5 times x, where x in this case is 3.05, or the input to the function is 3.05, minus 2e to the 1.5 times 2.95 divided by 2 times 0.05. And I'll title or label this as the approximate value for h1. And this ends up being approximately equal to 270.304638. Do a different color. And that's a general procedure for doing central divided difference method, given that h and given the point of interest, which is 3 for this example. Now we'll do our second iteration, where we say that h2 is 0.025. And again, that's the same as half of h1. So we'll say that our approximation for our derivative at 3 is going to be the same as f of 3 plus 0.025 minus f of 3 minus 0.025 divided by 2 times 0.025. And if we go through that math where we plug in those values into the original function, we end up with our second approximation for h2. That ends up being 270.114692. Let's do orange. So let's go ahead and look at what we've done so far. We have the true value, the approximate value for the first iteration, and the approximate value for the second iteration. So with the two approximate values, we would like to get a better estimate for our first order or first derivative. So if we do Richardson's now, and we use the equation that we derived before, we'll say that the derivative at x is approximately equal to, we'll scroll back up to see what it was, is equal to 4 times the second iteration minus the first iteration over 30. So this is 4 times the second iteration minus the first iteration divided by 3. And based on our highlighting, this is orange, and I think AV1 was yellow. Oh no, that's the true value. Green is the true value. There's the approximate value for H1. That's going to be 4 times 270.114692 minus 270 point, zoom out a bit, 304638 divided by 3. And if we go through that math, we will end up getting 270.051376. And this is due to Richardson's extrapolation. And note, the digits might be a little bit off compared to what you get on your paper, because it's possible when I wrote these originally, I did not include 6 digits. Maybe I used the true value, or as close to the true value as my calculator can handle, and instead of chopping or truncating or chopping or rounding the digits. But that's what you would get if you use more than 6 digits. And if we compare, let's remember what our true value was. Our true value was 270. Where'd it go? 0.051394. And if you compare that to what we just did, we see that we're really close. We have a lot of matching digits at that point. Let's go ahead and look at the results a little bit. So to summarize the results for, I'm going to say our approximate values for AV when H was 1, or when H was 0.05, the first iteration, we end up seeing that our relative true error, which again is the true value minus the approximate value over true value, and I'll leave it as a percentage, that ends up being 0.0938%, which is pretty good. But maybe you want to do better. So we decrease H. When we halved it, we end up seeing that our error gets roughly quartered, as we expect, based on our derivation in the previous lesson. But for Richardson extrapolation, when we use both of these different iteration values to help us estimate a new true value, that ends up being 0.0000659%. And obviously we can see that this is our winner here, because of how small the relative true error is compared to the approximations using just a simple value of H. And if you think about it, if we kept quartering this error by continuously halving H, it might take us a decent amount of iterations to get to this level of accuracy. But instead, we're able to skip those steps and just use the results from our 2 earlier iterations to get a much better estimate for our first derivative. I hope that this makes sense. If you have questions, please let me know. Leave a comment or message me on Teams or through email. I'll be happy to respond. And that's it. Thanks for watching. Bye, guys.